Today we're going to be learning about what are called homogeneous differential equations. And so the first thing that I want to share with you is actually something not really mathematical at all, but something about pronunciation. There are two sort of close to one another words in the English language, and those are homogeneous and homogeneous. Homogeneous, to be honest, is my understanding is sort of that it's a semi-archaic word that generally comes only out of science. Science is in general fine, but I think scientists in general are moving more toward the word homologous to be what homogeneous used to be. But for our purposes today, we're going to be talking about things that are homogeneous. Homogeneous means that you have things that have similar characteristics that are together in a group. So we're going to be looking at homogeneous differential equations, and I just kind of wanted to make sure that we all notice that there's an extra E there, and that means we get an extra syllable. So 5 syllables, homogeneous. Okay, so we're now going to be getting into the math on how we solve these things. Actually, what we're going to be doing first is looking at what a homogeneous differential equation is, and then we'll be looking at how we're actually going to go about solving them. So the definition for a homogeneous differential equation is that it's a differential equation that has this form, okay, where dy dx would be equal to f of y over x. And so very often, either on an IB exam or in general when we're solving something, the first thing that we need to do is we need to determine if something is homogeneous. Once we know if it is homogeneous, we can use our method to solve that homogeneous differential equation. So this example that I have right here, we're going to go through this one together, and then the next segment has 2 of them that you'll get to try on your own. The question for us becomes, can I take this differential equation as it's stated here and rewrite it like this? Is it possible for me to get dy dx on one side and then have, y over x be the variable that's happening in all of these things? And so what I need to do is I need to get dy dx alone. So the first step that I'm going to take here is I'm going to divide this x squared over. So I'm going to get this to be dy dx equals 3x squared over x squared plus 4xy over x squared minus y cubed over x squared. Okay? And I could certainly pretty this up a little bit. Let's see here. This first thing would just be 3. This next term would be 4 times y over x. And in this last one, I would wind up with y cubed over x squared. So as we're looking at this thing, I want to show that this thing is this form. Notice that the dy dx is now alone. Okay? And the question is this thing on the right, is this a function of y over x? And I think that one way we could do that is we can sort of look at it term by term. First, is 3 a function of y over x? And the answer to that is yes, it is. It's a boring function, it's a constant function, but this thing depends directly on y over x. Okay? This here, 4 times y over x, that's also a function of y over x. The only variable that's there is y over x. Now we get to this last thing here, and we might wonder, is that a function of y over x? And the answer is almost. I could write this as y over x squared. The trouble is there's another y out there, which means that this thing does not depend on y over x alone. It also depends on y. And so what we see here, if I write this whole thing out, this thing is not homogeneous. It's not homogeneous because at the end of the day, we had this extra y term that was out there. We were really happy about this, and we were really happy about this. We were even happy about the constant here. It was this extra y at the end that gave us trouble. So this is not a homogeneous differential equation, but this is the method that we use. We get dy dx alone, and then we see if we can write everything else in terms of y over x or powers of y over x. So now I have 2 examples here that you can go through and try on your own. If you'd like, work through the one on the left and then watch it along with me, and then work on the one on the right. So go ahead and give those a shot. So just like we did in the previous example, for this one on the left, we're going to start by dividing by x squared. So we'll have dy dx is 3 minus 4 times y over x plus y squared over x squared. This time I did the simplification all at once because this should be pretty straightforward. So, if I really wanted to make this explicit, I could write this out and show myself that this was, f as a function, f of y over x. I could do that by sort of putting parentheses around these things and just making it really, really clear to myself, hey, this thing truly is a function of y over x. Y over x is the only variable that would be happening here. Okay, so at this point we have shown that this first differential equation is homogeneous. So now we'll move over to the one that's on the right. I think the first step here is going to be to split this into two separate fractions. So this would give me dy dx equals x squared over 2xy plus y squared over 2xy. At this point, we can simplify each one of those rational functions just a little bit. This would give me x over 2y, and this would give me y over 2x. Okay, now remember, we still want to write this as a function of y over x. So something we could do here is we could make this 1/2 times x over y, and this could be 1/2 y over x, and this feels like we're so close because the thing on the second term is y over x, but the first one is x over y. So is there any way that we could make that y over x? Sure, we could make this y over x to the -1. And so at this point, we have shown also that this right one is also a homogeneous differential equation. So now that we sort of know how to tell if something's homogeneous, we need to come up with our method for how we're going to solve them, and that's where we're going next. So the core principle to solving a homogeneous differential equation is basically that if it's not already separable, there's a way that you can convert it into being a separable differential equation, which is amazing because separable differential equations are really, really easy to solve. It was like the first kind of differential equation that we ever learned about, and so converting things to be separable is really great. So the way that we're going to convert into being a separable differential equation is if, that's a big if you have a homogeneous differential equation, then you can use this substitution and it will be converted into a separable differential equation. Okay, so if you take either of those two previous problems that we had and use this substitution, you will be able to change the problem into something that's separable. Now keep in mind, when we do that, we're also going to need to change our dy dx. We're going to need to change those things as well. And the conversion that we're going to use is this one right here. Okay, and where that comes from is honestly, if you think about y equals vx, if you were to take the derivative of both sides of this, what you would wind up with is you would need to do a product rule over here. You'd have the derivative of v, which will be your dv with an x, and then you'd have your derivative of x, so v dx. So these are the conversion things that we're going to use. These are the change of variables that we're going to use when we have a homogeneous equation and we want to make it separable. Okay, so I've now got two examples of that, and we're going to go ahead and go through those two examples. All right, so because this problem starts out by telling us that it's a homogeneous differential equation, we don't have to start by showing that it's homogeneous. On the IB exam or in your math class, you might be asked to first show that something's homogeneous, but if the problem says find the solution to a homogeneous differential equation, you can kind of skip that step. So here's the method that we're going to use for this. We mentioned that we were going to use the substitution y equals vx, and similarly dy equals x dv plus v dx. Okay, so the first thing I want to do here is I want to sort of multiply this thing out. I want to first write this as, we sort of cross multiply, 2xy dy equals x squared plus y squared dx. Okay, and by the way, like quick comment here, the reason that homogeneous are called homogeneous, meaning that they have similar characteristics, is that when you look at this here, this is kind of like a second power expression. It has an x and a y. There are two things there. Over here, this is x squared, and this is also y squared. This is homogeneous, where the idea is that the degree of the homogeneity here is 2. This is like, like a second degree kind of thing. It's not critical that you know that, but I figured I'd throw it in, as I saw it here. So now I'm going to take these conversion factors that I have over here, and I'm going to use them to change the variables, right? And this is going to be a lot, but here we go. So I'm going to have 2x, and then I'm going to use that y conversion where this becomes vx, and then my dy, right? My dy here is supposed to be x dv plus v dx equals x squared plus, now I've got to use that y conversion again, This is going to give me v squared x squared dx. Now again, I know that this is a lot. There's a lot of variables running around here, but I've converted from two variables x, y into two variables v and x. And the exciting part is that I promise, if this really was homogeneous, then this is going to be separable, and we'll be able to separate these variables. Before I do that, I need to simplify some things. In general, what I'm going to want to do is I'm going to want to take this and distribute it into these things, and take this and distribute it into these things. Okay, so on the left-hand side here, it looks like I'm going to have 2x cubed v dv plus 2x squared v squared dx equals x squared dx plus v squared x squared dx. Wow. Okay, so here I am. We're gonna need some more space here. I've got this thing, and remember, the claim is that this is separable, right? So if this is really separable, it means that I should be able to move all of the x's to one side, all of the v's to the other side. And the method that we always used for that before was we would get all of the like dx's on one side and all the dv's on the other side, and then sort of let things fall where they will. So I think that what we're going to want to do here is we're going to want to take, like, this side is already saying that it's the v side. Let's take this dx thing and move it over here, because these are already dx's. That at least lets me get all the dx's on the same side, okay? So let's see here. That gives me 2x cubed v dv equals x squared dx plus v squared x squared dx minus 2x squared v squared dx. All right, so now I've sort of declared that the right side is the x side and the left side is the v side. So in theory, I need to get all the v's on the right over to the left and all of the x's on the left over to the right. Okay, so lots of times for me, I've found that it helps to sort of factor things, to factor all the sides as much as you can, because it helps you to see which factors you have to work with. Now the left side is already, like, it's already really factored. We've got 2 times x cubed times v times dv. I could very easily divide any of those pieces to move it to the other side. So notably, I'm going to want to move this guy over in just a minute. On the right side, let's look at what we have that can be factored out. I'm noticing that there is an x squared in all of them, so I can factor that x squared out. I'm also noticing that there's a dx in all of them, so I'm going to factor that dx out. Okay, and I'm actually going to factor that one out at the end, because we always like to have those things at the end. All the other stuff that's left, there's basically a 1 from the first term, there's a v squared from the second term, and there's a minus 2v squared from the third term. So when I go and clean all this up, I get 2x cubed v dv. Remember, these are all factors. On the right, I have x squared, 1 minus v squared, and dx. Okay? Now, remember I said that this thing was going to be separable? At this point, we realize that the right side is the x side, the left side is the v side, and so we identify what needs to move, right? I need to move the 1 minus v squared over, and I need to move the x cubed over. So I'm just going to divide those two things to their other respective sides. So here I'll have 2v dv, so 2v over 1 minus v squared dv, equals x squared over x cubed dx. And I mean, I don't know if you guys are seeing this, but like, wow, it really was separable. All of this like math soup up here all managed to simplify into something absolutely separated. And now that these two sides have been separated, what we can do is we can integrate each of those sides just like we always used to do in a separation of variables type of differential equation. So my next step here is going to be to integrate both sides of this thing, right? So on the left side, I'll integrate with respect to v, and the right side, I integrate with respect to x. I suppose that right side should have been simplified first, but I think we can see that. This left side is a u substitution, but I think it's a fairly easy one, so I'm hoping we can sort of skip that step. This is going to be the negative natural log of 1 minus v squared. And on the right side, this is basically just the integral of 1 over x, which is the natural log of x plus c. Okay. Our next step is going to be that we want to, we basically want to isolate v, because remember that ultimately we want our answer to be of the form y squared equals f of x. And remember from the beginning of the problem that y was vx, which means v is going to be y over x. So at some point, I'm going to want to take this substitution and put it in for v, but I don't really want to do that yet. I'd really like to get that side cleaned up before I throw a fraction into it. So I'm going to start by multiplying the negative to the other side. So I'm going to have the natural log of 1 minus v squared equals negative natural log x. I'm going to keep putting plus c, just because the constant will absorb that negative. I also want to take this negative 1 that's here and use the properties of logarithms to put it up here. Okay, so at this point I'm going to have the natural log of 1 minus v squared equals the natural log of x to the negative 1 plus c. Now we're going to do a neat trick that we've done numerous times before. I'm going to exponentiate here, right? So I'm going to make both sides, the power of e. And when I do that, on the left-hand side, I'll wind up with the absolute value of 1 minus v squared. On the right side, I'm going to wind up with cx to the negative 1. And real quick, why that happens. This thing can basically be split into e to the natural log x to the negative 1 times e to the c. Well, e to the c is just going to turn into some other constant c, and for this one here, the e and the natural log effectively cancel out, leaving me with x to the negative 1. Okay. Also at this point, I can drop the absolute values, because all those absolute values are doing are sort of changing that value between being positive and negative. And we can also change the value between being positive and negative by thinking about this value c. Okay. At this point, that left side has been significantly cleaned up, so I want to go ahead and plug in that y over x that I was mentioning earlier. This is now 1 minus y squared over x squared equals cx to the negative 1. Remember, I want to solve for y squared, so I want to get that y squared alone. I'll multiply through by x squared. X squared minus y squared equals cx. And then the last thing I need to do is move a couple of things around here. I'm going to wind up with y squared equals x squared minus cx. And honestly, because it's c, we could have made that plus cx if we wanted to. This is the general solution to this homogeneous differential equation. You can see that this is a really, really long and algebra-filled process, and it's really, really easy to make mistakes along the way. In fact, I made a mistake about 3 minutes ago, and I had to go back and rewind the video back to that part and fix that. So you really, really, really need to be careful with your algebra as you're working through these. I know this video has already been really long. I do have another example after this one, so if you're looking for another one to practice, go for it. That one is going to involve finding the value of c, finding a particular solution. So I hope to see you in that one. So the second example is going to be a little bit more straightforward than the last one was, but we are going to need to deal with finding the value of c at the end because we are given an initial condition here. We're given that y is going to be 2 and x is 1. So if you're feeling bold, give this one a try on your own. It should be a little bit nicer than the last one. So let's see. The first thing that we do is we sort of cross multiply, right? We've got our x dy equals x minus y dx. And then we're going to use that change of variables that we had discussed before. We're going to use that y equals vx, which means that dy is v dx plus x dv. So we're going to go through and substitute those things in, right? So this will be x times v dx plus x dv equals x minus vx dx. Our next step we had mentioned was this idea of distributing everything through this. So we'll wind up with xv dx plus x squared dv equals x dx minus vx dx. And the next step that we discussed was this idea of getting all of the dx's to one side and all the dv's to the other. So the only term that we have here that's sort of out of place is this guy right here. And something I like to do is sort of think, is this going to combine with anything on the right? When I subtract this over, it's going to combine with this term right here. And so by doing those at the same time, I can sort of save myself a step. Right, when this gets over here, I'm going to wind up with minus 2 vx dx. Okay. We had discussed then that our next step is we really want to factor both sides so that we can divide things as necessary. So the left side is already factored, x squared and dv. On the right side, there's an x I can factor out, there's a dx that I can factor out, and when I pull those out, there's just a 1 left from here and a minus 2v from here. Okay. Now that I've done all of that, I can divide over the things that are sort of on the wrong side. So I'm going to move this 1 minus 2v over, and I'm going to move this x squared over. So I'll now have dv over 1 minus 2v, and on the right side I'll have x over x squared dx. Okay. Now that I've separated, I can integrate both sides. The left side technically requires a u substitution. You can either work that out or you can sort of, see it on your own. It's a fairly straightforward one. This is just going to be negative 1/2 the natural log of 1 minus 2v, and on the right side I will have the natural log of x plus c. Just like we did in the previous problem, I eventually want to get to the point where I'm using the substitution v equals y over x. But I'm not quite ready for that yet. So I'm going to multiply by negative 2 to try and simplify the left side before I bring that substitution back into it. When I multiply by negative 2, we'll get negative 2 natural log x plus c. I'm going to take this negative 2 and move it up as the exponent. So next up here we will have the natural log of 1 minus 2v equals the natural log of x to the negative 2 plus c. To get rid of the natural logs, we're going to do our exponentiation idea. And this is going to give me 1 minus 2v equals cx to the negative 2. And again, there are multiple steps that are happening here. One of them is that on the right side, I'm separating this out into two expressions, where e to the c is going to simplify to c. Here, the e and the natural log are going to cancel, leaving me just the x to the negative 2. And the reason I got rid of the absolute values is that any negative or positive or negative that this would have had can be absorbed by the c. Now that I've gotten that far, I'm going to use my substitution. Right? We can say 1 minus 2y over x equals cx to the negative 2. Multiplying through by x, we get x minus 2y equals cx to the negative 1 now. We're almost there. Let's see here. If I move the cx to the negative 1 over here and the 2y over to here, we can just divide by 2 and get 1/2 x plus cx to the negative 1 equals y. So this is our general solution. Now that I have that general solution, I just need to plug in the initial conditions so that I can find the value c to get my particular solution. From the beginning of the problem, we were given that y was 2 when x is 1. So I'm seeing this to be 1/2 plus c equals 2. That means c has to be 3/2. And so my final particular solution, y equals 1/2 x plus 3/2 x to the negative 1. So, sorry this was a really, really long video. These homogeneous differential equations often have a lot of algebra with them, so they are kind of time consuming and you do need to take care with your work. So best of luck when you practice your problems on these.